Hello and welcome to my talk about sensor fusion, which is one of the many topics discussed in the book Planetary Rovers, Robotic Exploration of the Solar System by Ellery. I will start this talk off with an explanation of the basic principles of sensor fusion, and I'm going to continue with some examples of how sensor fusion is being used. After that, I will present the main problems and the challenges that the sensor fusion approach faces and has to overcome. Lastly, I will talk about the different categories of sensor fusion and the different methods used to perform sensor fusion. The basic idea of sensor fusion is to merge information from multiple diverse sensor modalities. This can either be redundant information of similar modalities but with different fidelities, or complementary information of different modalities. This is done to achieve a more precise prediction of what the environment around the system is like, and to reduce disturbances and noise in the measurements. In the shown example, data about the translational and rotational movement of an object is captured via 3 different sensors. An accelerometer that measures acceleration, a gyroscope measuring rotational velocities, and a magnetometer measuring the surrounding magnetic field. This collection of sensors is called an inertial measurement unit, or short an IMU, and is capable of producing the position and orientation of a system relative to a fixed starting point. Such a sensor suite can typically be found on most satellites and of course rovers, but also in more common systems like cars and even smartphones, and is very useful for determining the pose of such a system. While each of the individual sensors of the whole suite has its own flaws and disadvantages, when utilizing sensor fusion to merge the collected data, many of those, especially noise and disturbances that only affect singular sensors, can be overcome. With the resulting data, a precise understanding of the movement and attitude of the system can be achieved. Additionally, not only traditional sensors can be used as an input to sensor fusion, but also mathematical models that describe the environment or the state of the system. Now let's come to the first example that should be quite familiar to most people, the car. Especially modern cars and cars that are semi or fully autonomous have a lot of sensors built into them. Some of those sensors might be cameras, radars, lidars, ultrasonic sensors, the already mentioned IMUs, or other maybe less interesting ones like temperature and pressure sensors. And since all individual sensors can only capture certain aspects of the surroundings of the car, all the gathered data is merged to get a precise sense of the environment. This can be done using different approaches, with the one mentioned here being the Kalman filter, that I will later come back to. The result then is a set of different types of information about static and dynamic objects in the environment, the drivable area, regulatory information, like for example lines in the street, road signs, or traffic lights. This information can then be further enhanced by using classification algorithms to determine what exactly those static and dynamic objects are, if they are cars, trucks, bikes, pedestrians, or simply trees or other things. Another interesting example, especially from a biological standpoint, is a ventriloquist. For everyone that did not know, a ventriloquist is an artist, commonly a comedian, that typically performs on stage alongside their puppet. The act most often consists of a conversation of some sort between the artist and their puppet, where the artist makes it seem like the puppet is talking, while they themselves are the ones talking. Here, the human brain tries to match the voice it hears to the movements of the puppet's mouth via a phenomenon similar to sensor fusion. Since for most people, visual information is more accurate and reliable than acoustic information when dealing with directionality, the voice actually seems to appear from the puppet's mouth, even though everyone knows that the puppet cannot speak. This kind of confidence measurement assigned by the brain to the visual and acoustic data are also used in common sensor fusion approaches to differentiate between different sensor fidelities and data quality levels. Such confidence values can also be assigned dynamically, depending on the environment and the sensor measurements over time. Now that we know how sensor fusion works and how it can be used, we need to talk about some problems and challenges that need to be overcome before sensor fusion can be applied to sets of data. Throughout this talk, we have already encountered multiple different sensors, like accelerometers, gyroscopes, and magnetometers, that are part of an IMU, and also multiple sensors that are focused on imaging, like radars, lidars, ultrasonic scanners, and cameras. But as you probably know, and as it is shown here, there are plenty more types of sensors that each measure different physical properties. But they do not only measure different things, they also produce outputs and datasets of different forms and different dimensions, ranging from simple one-dimensional values like temperature data to n-dimensional values like poses or other complex sets of data. Additionally, all sensors have different transduction mechanisms, sensitivities, bandwidths, spectral directivity profiles, and data processing rates. When using multiple sensors in one system, they will also be placed in different locations, creating the need for transformations that are able to represent all datasets from a common viewpoint. Once the sensor data has been gathered and transformed, the data points of different sensors that correspond to the same object additionally need to be registered and matched. Overall, it can be said that datasets from widely differing sources and forms of representation need to be merged into one unified representation medium so that it can be used efficiently. Now I will present the different versions of sensor fusion. There are two main factors by which sensor fusion can be categorized. The first one is the level at which the fusion happens. This basically means that data can be merged before, while, or after it is being processed. In this example, the raw data coming from the camera and the radar can immediately be merged, which would be called a low-level fusion. The raw data can also first be processed using some sort of object detection algorithm, and the resulting object data can then be merged, resulting in a mid-level fusion. A high-level fusion can be performed by even further processing the data before merging it. This could, for example, be done using a tracking algorithm that tracks the individual objects that have been successfully detected in the previous step over time. While the complexity of the fusion itself rises with the amount of processing done beforehand, the size of the datasets that need to be merged is ideally reduced in each processing step. But mid- and high-level fusions can not only suffer from complex fusion processes, but also from measurement errors that propagate unnecessarily far through the system before ideally being eradicated by the fusion. A second differentiating factor is the time and place where the fusion happens. The most straightforward approach is to take all datasets from all sensors and centrally merge them all at once to achieve one final resulting dataset. This would be called a centralized fusion. A different approach would be to merge data where it is created with neighboring sensors and then merge the resulting datasets from those sensor clusters into one final single dataset. Another way of fusing data is to merge the data of all sensors pairwise with the datasets of all other sensors, and merge all those resulting datasets into one final set. Obviously, one can use different approaches to merging data in different parts of a system, resulting in a mixture of the described variants. For example, a humanoid robot might have multiple sensors in each of its limbs, whose data could be merged locally in a decentralized or distributed manner. Then, after processing the fused data in each limb, the datasets of each limb could be merged into one single dataset in a centralized manner. In the end, most real systems won't strictly use one category of sensor fusion, but will use whatever works best for each individual subsystem. Lastly, I will now briefly present a few algorithms and methods that are used to actually perform the fusion, and additionally go into detail on two of those variants. All the presented methods have a similar and rather simple approach, which is to find some sort of confidence factor for each sensor that will then be used as the weight for the corresponding dataset in the fusion process. These confidence factors can either be fixed or be calculated on the go, depending on the environment and the measurements over time. Coming back to the example of the ventriloquist, the human brain can also assign confidence values to the data it receives, depending on the environment itself. While in a well-lit room, like in the example, the brain would give a high confidence rating to the visual information it receives. But when facing a pitch-black environment, acoustic data would receive a huge boost in its confidence rating compared to visual data, and vice versa if facing a very loud environment. The first method I am presenting is the Bayesian estimation, which uses Bayesian probability theory and therefore conditional probabilities to calculate how likely it is that the environment has certain properties given the sensor data and possibly also other previous knowledge. The next method is the Dempster-Shafer theory of evidence, which is a generalization of the Bayesian approach, but it distinguishes between belief and plausibility, where belief is the sum of all data directly supporting a hypothesis, and plausibility is 1 minus the sum of all data directly contradicting the hypothesis. Therefore, other than with normal probability theory, a dataset that does not directly support a hypothesis does not have to automatically contradict it, but can simply just not affect the hypothesis at all. Another method is to utilize fuzzy logic, which allows to handle partial truths, with the truth value lying in a range between completely false and completely true, while in standard Boolean logic only two values are possible, either true or false. This approach can also deal with non-numerical information that is vague and lacks certainty. Lastly, also neural networks and, for example, deep learning can be used to fuse data in a very dynamic and efficient way. How exactly the fusion happens is not well defined in this use case and varies from one application to another, but can be influenced by how the network parameters are chosen. Obviously, this approach faces typical challenges every neural network approach has to deal with, like choosing a suitable learning algorithm, supplying sufficient training data, being able to provide enough computational power to firstly train the algorithm and eventually using it onboard the system, etc. Now I will discuss two approaches in a more detailed way. I will start off with the simplest and rather static approach, which is the weighted average. Generally, the weighted average x dash can be calculated as seen here, where each data point x is multiplied with its corresponding weight w, and the sum of all weighted data points is then divided by the sum of all weights. In the special case that all weights sum up to 1, this simplifies to just the sum of all weighted data points. When applying this to the sensor fusion approach, the data points x resemble the outputs of the sensors, that in the simplest case are just one-dimensional values, and the weights w correspond to confidence factors that are applied to each sensor output. When only using the weighted average and no additional computations, the confidence values have to be initialized once and then keep that value over the whole lifetime of the system. This can lead to problems if a sensor develops any problems or has any malfunctions in its operation lifetime. Many other sensor fusion approaches solve this problem by recalculating the confidence values on the go in relation to the performance of the sensors and the changes of the environment over time. One of those, and probably one of the more popular approaches, is the Kalman filter. It is able to estimate properties that cannot be directly measured while reducing measurement errors optimally. When dealing with dynamic properties, a mathematical model can be added to the filter to take dynamic interactions between measured properties into account. This mathematical model can, for example, consist of the equations of motion that can precisely predict the position and velocity of an object or the system itself. The algorithm behind the Kalman filter is shown in this chart and can be split into 4 steps. 1 step for initialization and 3 steps that are performed recursively. The first step, or step 0, is the initialization. Here, the initial state of the system, which could for example be its pose relative to Earth, is defined. This initial state is then used to immediately predict what the state should be like at the next time step using the mathematical model. Therefore, the recursion is entered at step 3, which is the prediction. The predicted state and the new sensor outputs from step 1 are then used to perform step 2, the update. Inside the update, firstly, the new Kalman gain is calculated. The Kalman gain essentially holds all confidence values that will be assigned to the individual measurements. Using this Kalman gain, the current sensor measurements and the prediction from the last iteration of the algorithm, the current state of the system is estimated. So when in normal operation mode, first all measurements are gathered from the sensors. Then, the new Kalman gain is calculated and used to estimate the current state of the system, utilizing the collected sensor output and the last prediction. The calculated state of the system is then fed into the mathematical model of the system to predict the next state. This way, the confidence values of all measurements are always adapted depending on whether they coincide with the predicted system state or not. This ensures that faulty sensors are mostly disregarded over time, and accurate sensors have a bigger influence on the estimation of the current state of the system.